Hello, this is homework number 2 for EGR 480, the 4-bit adder. After we have mapped our ports, in which you can see we used 9 switches and 5 LEDs, we can start our behavioral logic. We have a 4-bit sum that we use to store our added 4-bit numbers, and then we have a 1-bit carry out. We then import the adder.vhd file and we map our ports. We map switches 3 to 0 to the variable A. We map switches 7 to 4 to variable B. And then we have our 9th switch mapped to carry in. Then we just have our logical signals connected. Lastly, every clock cycle we set LED 4 equal to the carry out value, and we set LEDs 3 through 0 to the value of sum, which is 4 bits. So the next thing we have to look at is adder.vhd. So as you can see, once we have our ports mapped, we have to create a 5-bit result signal, and then we have to add A and B together, both of which have been resized to 5 bits to allow us to also add the carry in bit. Now, once we have our 5-bit result, we have to map it back down to 4 bits to get the sum, and we have to set the 5th bit equal to the carry out. This is the actual logic that drives our 4-bit adder. Lastly, what I have to show you is the test bench. So the test bench is very simple. We go through a series of numbers, add them together, and verify that the result and carry out flags are set correctly. In our simulation, you can see that happening. When A is 1 and B is 2, the sum is equal to 3. When A is 5 or 10, and when A is equal to A, which is 10, and B is equal to 5, then the sum is equal to 15, which is F. Lastly, when A is 6 and B is 9, and the carry in flag is set, we will have a carry out flag set, but no sum. What this means is that the total sum is 16. So we can see this in action on our FPGA. When we have 1 in the A and 1 on the B, we have a result of 2. If we were to add 2 to A, now we have a result of 4. And if we were to set all 8 of A and B together, we have a maximum result of 15. Setting the carry in will give us a much larger result of 31, which is the maximum possible result in 5 bits.